Welcome back. This is Mrs. Rewright with Geometry Honors. Today's lesson is 5.2, Use Perpendicular Bisectors. Alright, so BD is a perpendicular bisector of AC. Find AD. So it's saying that BD is a perpendicular 90 degrees, bisector, cuts it into two equal parts, of AC. Okay, find AD. Well, what do we know? Okay, if this is a perpendicular bisector, then what is this? Isn't this going to be reflexive? So by side, angle, side, we know that these two triangles are congruent, therefore corresponding parts of congruent triangles are congruent. So set this equal to this. 3x plus 14 equals 5x. Subtract 3x from both sides. 2x equals 14. Divide by 2 on both sides. X equals 7. Okay, and then what are we solving for? Are we solving for x? AD. So plug back in. 7 times 5? 35. Good. Makes sense? Always go back to what was I actually solving for, because you get excited when you solve for x. You're like, oh, I'm done. But you're not always done. Sometimes you have to plug back in. Alright, so the perpendicular bisector theorem skips the reflexive and basically just goes to, okay, if it's a perpendicular bisector in a triangle, then it's isosceles, right? So you don't have to do reflexive, therefore corresponding parts of congruent triangles are congruent. It's just like a step that gets skipped. But if you don't remember that, you can always do what you do know, which is reflexive, therefore corresponding parts are equal. Alright, so what segment lengths in the diagram are equal? So we know for sure. So over here, okay guys, do you see how YV is congruent to ZD, right? These are congruent. So what segment lengths in the diagram are equal? Well, we know for sure those are equal, right? So wouldn't this be like the converse of what we were just doing, the perpendicular bisector theorem? So this must go through here and must be a perpendicular bisector. Because these are equal, then this must be a perpendicular bisector, making YX congruent to ZX, right? So it says that it bisects it, so that XY is congruent to XZ, right, what I just said, because on the perpendicular bisector, so by theorem 5.2, the diagram shows that they're equal. These are equal, and these are equal shown in the diagram, right? Alright, so is V on WX? Yes, because since these two are equal, then this is on it, because this is a perpendicular bisector, right? Make sense? If these two were not equal, then no. But the fact that these are equal, then yes, it is a perpendicular bisector, therefore it goes through V. It's the converse of the perpendicular bisector theorem. What segment lengths are equal? MN is congruent to ML, right? Well, if those are equal, then M is on it, right? This is a perpendicular bisector, therefore this and this are equal. Since these are equal and this is perpendicular, then these are equal, right? So it says NJ equals LJ, so these two are equal, right, because it's bisected. It says that NK equals LK, NK equals LK by the perpendicular bisector theorem, and ML equals MN shown in the diagram. Make sense? Find NK. Alright, so once again, these are equal, therefore this is a perpendicular bisector. Since this is a perpendicular bisector, these are equal. They want to know what is NK. Well, NK is equal to this. Set them equal and solve. Subtract 4x from both sides. 2x minus 5 equals 1. Add 5 to both sides. 2x equals 6. Divide by 2 on both sides. X equals 3. Plug back in. 3 times 6 is 18 minus 5, 13. is, explain why M is on JK. Because these are equal. Since these are equal, then this is a perpendicular bisector. So therefore, M is on it, right? Because then these are equal. These are equal. This is equal to itself. Since ML equals MN, M is equidistant from N and L. So by the converse of the perpendicular bisector theorem, M is on the perpendicular bisector of NL, which is JK. 3 snack carts sell frozen yogurt from points A, B, and C outside of a city. Each of the 3 carts is the same distance from the the frozen yogurt distributor. Find a location for the distributor that is equidistant from the 3 carts. Okay. So, to do this, we actually need to find their perpendicular bisectors. So first I'm going to make segments between these. Actually, I should do them in different colors. Okay. So, here is your triangle, right? And we want to know where the frozen yogurt distributor should be. So basically, we want it to be a point that is the same distance for cart B, for cart A, and for cart C to be able to walk to. So we want to know where's smack dab in the middle of all 3 of these guys where they're all walking the same distance. So we need to do a perpendicular bisector. So let's get out our math tools. Ooh, it doesn't have a compass on here. That's not cool. Alright, so I'm going to do this on a piece of paper, so bear with me. Alright guys, so we are back. So I just made my 3 points. So once again, I'm going to connect the 3 points so that I can turn it into a triangle. And I'm going to do this in different colors. Perpendicular bisectors. So how I do a perpendicular bisector is I put the sharp point on the vertex and I open it up a little bit more than halfway of the segment, okay? I do an arc above and an arc below. Then I move my point to the other vertex of the segment and I do my arc above and arc below. And here you can see I need to actually extend this one a tiny bit. There we go. So now you can see that they intersect here and here. So I can draw a line connecting these 2 points. And this is a perpendicular bisector of AC. So now I'm going to move to another side. So I'm going to put my point on this A. I'm going to open it up a little bit more than half, go like this, arc above. I didn't do my arc below. So let's do my arc below. There we go. So now I have here and here. And I'm going to connect those. And that is a perpendicular bisector of AB. And then for my third side, my BC, put this on C, arc above, arc below, arc above, arc below. So that's here and here. And when I connect those, that's my perpendicular bisector of that way. So where these 3 perpendicular bisectors meet, right here, this point of concurrency of my 3 perpendicular bisectors is the central meeting point. So basically what this is saying is that my distance from A, from the stand A to the distribution center should be the same as the distance from B to the distribution center, which is the same as the distance from cart C to the distribution center. So all of these guys have to walk the same distance. All right, so something that we are going to be learning in a little bit is called Pamaseco. Pamaseco. And P stands for perpendicular bisectors. And what's important about your perpendicular bisectors is that they meet at the circumcenter. Okay, they meet at the circumcenter, and the distance from the circumcenter to each vertex is equal. Okay? So, as we learn more and have more and more lessons, we're going to be learning about these other relationships. So, for instance, A stands for the angle bisectors. They meet at the incenter, and we're going to learn all about that tomorrow. But for today, all we know so far is that the perpendicular bisectors meet at the circumcenter. Their point of concurrency of the perpendicular bisectors is called the circumcenter. So this right here is the circumcenter. And the circumcenter, from the circumcenter to each vertex, is equal. Okay, so a real-world example where this would be something that you guys could do. You could pull up a Google map of the area that you live in, and you can put a dot or vertice at your house and one at two of your friends' houses. And then you can actually find out the perpendicular bisectors to see where a good central meeting point is. So if you guys are all walking or riding your bikes or skateboards, you can see, okay, well, this park is really the closest to all three of our houses. If your point of concurrency is in the middle of an intersection, please do not meet there. Meet at the safest nearby location, okay? So this is how you calculate or figure out how you find the circumcenter. All right, so moving back to our flip chart. Theorem 5.4 shows that you can find a point equidistance from 3 points by using the perpendicular bisectors of the triangle formed by these points. So it's really just kind of talking you through what I just did. Let me plug my computer in. Sorry, guys. 1 second. All right. Oops. There it goes. All right. So now it's saying, what if hot pretzels are sold from points A and B are also from a cart at point E? Where could the pretzel distributor be located if it is equidistant from those 3 points? Sketch the triangle and show the location. Okay. So, there's a pretzel store. Okay, so it's the same thing. They're just saying that A, B, and E are your 3 points, and they want to know where is going to be the location that's best for these 3. So we're going to take out another piece of paper. We're going to duplicate this on our paper. So we have A, B, and E. I'm going to flip back so that you guys can see what I'm doing. So once again, the first thing I'm going to do is I'm going to create this triangle. Okay. Now, I'm going to find arc above, well, a little bit more than half, okay. Arc above, arc below, arc above, arc below. Here to here. Perpendicular bisector. Moving right along. Next one. Open it up a little bit more than half. Arc above, arc below. Arc above, arc below. This one's green. There and there. perpendicular bisector. Next side, a little bit more than half, arc above, arc below, above, arc below, extend that one a little. Perpendicular bisector. Alright, so the three meet here. The circumcenter is here. This point right there should be equidistant to all three vertices. Alright, are you guys understanding this? Alright, so moving back to our flip chart, we are going to reveal this. Let's shift this down a little. Alright, so that's where they say the pretzel distributor should be, and it looks just like that on our example. That is everything for today's lesson on 5.2, using perpendicular bisectors. I hope you guys enjoy the lesson. Please like and subscribe and have a wonderful day.